I'm just going to get to the point. So the setting is you have a distribution and it's on a discrete domain. So none of these continuous distributions. Okay, this is all very discrete. And we're going to use little n. Okay, let me just see the hands. Little n is the size of the domain. And we're going to assume that the distribution is given to you like a black box. You push a button, you get a sample from P. Okay, and each sample is ID. Right, so that's the model. And we're thinking of n as being really big, really, really big. And we're going to use pizza by, so this is standard. We're going to use pizza by to denote the probability that P gives to the element I in the domain. And we're not making any assumptions on P. Okay, so, you may think it's Gaussian, Lipschitz, maybe, but we're not going to assume it. Okay, so we're going to actually try to test that these things are true. Okay, so here's the thing. You're given a distribution on a really big discrete domain, and you need to know things like what's the entropy? What's the support size? Is it close to uniform? Is it close to Gaussian? Is it close to Zipf? There's all sorts of questions you could ask about a distribution. And these are sort of basic questions that sort of every field asks these types of questions. So how can we answer these? So we're going to focus today on properties of shape and more on shape of the distribution. Okay, so what do I mean by shape? Well, I don't mean things like entropy or support size, which don't seem to have anything to do with how the distribution is moved around, or whether like pi and pi plus 1 are close to each other or not. I do mean things like, is it monotone? Can it be described by a k-flat distribution, like a k piecewise constant function? Is it p-modal? Does it go up and down p times? So these feel like properties of shape. I don't actually have a precise definition that like a formal logician would be proud of what I mean by shape. This is sort of some examples. Yeah.
The number 1 to n are listed in order at the bottom.
Yes. And yes, right.
The differences are equal at least. I mean, the pi and pi plus 1, I mean, they're equal. There's some one-dimensional distance on them.
Yeah, so I'm thinking of this as being like, this is the case where you can think of the domain as being a totally ordered domain. I'm going to spend the first half of the talk on those kinds of domains where it's totally ordered 1 through n. And this is kind of the picture of what you would expect that things going to watch it. Okay, cool. Okay, now, so the key question for this talk is how many samples do you need in terms of the domain size? And the big question is going to be this. You could learn the distribution, like you could estimate the probability of each domain item. And learning the distribution would require something we know requires theta of n over epsilon squared samples. So you could just learn and you could answer all these questions that way. Okay, but the question is, do you have to do that? Or can you do something that's sublinear in the domain size? Now, remember, we're not assuming anything a priori about this distribution. So who knows? So that's our big question. Can the sample complexity be sublinear in the size of the domain? And let's start with a simple question asking whether the distribution is the uniform distribution. The complexity of distinguishing the case when P is actually the uniform distribution from the case when P is epsilon far in L1 distance is root n over epsilon squared. Okay, so here's a lower bound. Here's why it has to depend on root n. Here's the uniform distribution, and here's a distribution where we just pick half of the elements in the domain at random and assign them probability 2 over n. Okay, and now you start getting samples from your distribution. It's either this case or this case, you have no idea. Now the names of the elements don't tell you anything because these were picked randomly. So there's nothing special about the names. So you can't use the names somehow in your algorithm to decide if this is uniform. This can be made precise, but this is the idea. Actually, the only thing you can use is collision statistics. Because that's the only time you start getting information here. And the thing is, you're not going to see any collisions at all in either case until you see something like root n samples. So and here you will see collisions a little bit earlier than you would here. So then you can distinguish those two. But it does give you a root n lower bound. Okay, so that's why root n is, that is an easy enough thing that I can explain in a slide for why you need root n. There's more, if you want to get root n over epsilon squared, you have to work a little harder. So there's like a whole history on uniformity testing. It's been studied since 1996. Goldwasser and Ron gave actually noted that there's this problem of distribution testing and then said, well, since, I'm just, well, since you're not going to get polynomial time in log of n, this is not a good field. So that was the end of the paragraph. And then they moved on. They promptly forgot that they wrote this seriously. And I reminded Oded at his birthday party. He had forgotten, everybody had forgotten. I didn't realize, like we had just found it. Anyway, so then kind of Goldreich and Run implicitly found by looking, they were trying to solve property testers for expander graphs. And they gave a way of doing this in root n over epsilon to the fourth. Actually, they showed it in L2 distance, but if you just take their technique and see what it says for L1 distance, that's what you get. So there was more work. Paninsky gave tight bounds by looking at, instead of collisions, looking at the number of distinct elements. And he had to make some assumption that epsilon, it's like a minor assumption that epsilon's omega n to the -1/4. But then Chan et al. And Diakonikos et al. Gave a different estimator based on a chi-squared-like test that's optimal for all settings. And then Diakonikos, Gouliakis, Peebles, and Price showed that the collision-based tester is also optimal. And then they showed that the plug-in tester, that's the one that that's kind of really weird because that's actually trying to learn the probabilities of each. It's just estimating the probability of each element based on the sample, but they're only taking root n samples. So it's kind of going to be bad on all estimates. The plug-in tester is also optimal. And furthermore, that plug-in tester has really good confidence, really good dependence on the confidence. So it gets better than, usually we do this thing where you say, okay, I need log 1 over delta. So they get something better than log 1 over delta in terms of their confidence. So the summary is, what you need to remember is basically all methods work to get you root n over epsilon squared, but plug-in is actually the best if you're worried about your confidence. Okay, summary. Okay, good. But there's some not so great news. So what that slide was about was distinguishing perfectly uniform from epsilon far from uniform. And you're like, I knew the thing wasn't uniform. I just want to know if it's close to uniform or far from uniform. What is the sample complexity of that? I want root n over log n. I want root n for that. Too bad.
Sorry, I didn't catch the difference. Say it again.
So what I had before was distinguishing P minus U is 0
Versus epsilon.
and versus allowing it to be tolerant.
Epsilon.
This is tolerant property testing where I still have to pass if it's close, but I have to fail if it's far. And the variance,
Or like two-sided.
yeah, it's true, right. And so we call this tolerant property testing, because of the two-sided, right? And this problem is already theta n over log n, still sublinear. It's still B-flirting, but it's not root n anymore. Okay, and it's actually really bad. I think there's an example. Well, I don't know for n over log n what the example looks like, but for the case of for slightly weaker bound, at least, you can show that even distinguishing epsilon close from 1 minus epsilon far means n over log n. So it's terrible.
Is there any assumption on the epsilons for this lower bound?
I think they're like constant. No, I don't think so. I didn't give the dependence on epsilon, so I don't know. It's probably not tight, but I don't know that. I don't even know what I have to say, whether it's tight or not tight. So, okay, there are some. Okay, let me say that I'm sure that there is some dependence. I just don't remember what it is. And there's some works that you probably put together and get something of it. Okay. All right, so tolerant testing hard. Let's move in a different direction. Let's go back to intolerant testing. I only need to distinguish P equals Q from P far from Q. So it's back to intolerant. But now I don't care if the thing is uniform. I have my other favorite distribution Q. I want to know is P equal to Q or far from Q? And it turns out that is not much harder. Like Q versus uniform is not much harder. So in arbitrary Q, it's still root n over epsilon squared, and the tolerant version is still n over log n. So it doesn't actually matter that you can pick the nastiest distribution you want. You may think uniform is pretty simple, so of course it's going to be root n, but you can come up with the nastiest Q you want. It's not going to be worse than uniform. And there's a whole bunch of works. Some of them work by reducing to uniformity testing. some work by looking at the estimators directly and analyzing the estimators. But the summary is theta root n over epsilon squared samples via lots of types of estimators or lots of types of reductions. Okay, so this was, that was for arbitrary domains, but I want to now focus on these domains that you asked about earlier, just the domain that's completely ordered. The numbers, the integers 1 through n. Okay, so these are totally ordered. What did I do? Oh, good. Okay. All right. I want to focus on monotone distributions. And why monotone distributions? Because they make a lot of tasks easier. For example, learning in the presence of a monotone distribution can often be easier. Estimating the entropy of a monotone distribution is a lot easier, like exponentially faster. Testing independence of joint distributions is a lot easier when you know they're monotone. Yeah.
Just a question about the previous slide. So you said you're only going to focus on ordered domains now. So what was the previous, previous results were?
This was kind of domain independent.
So the n, wasn't it the?
It's the size of the domain.
Oh, 60. Okay.
Yeah, thanks. So the n is the size of the domain, but here we don't use anything about the structure of the domain.
I see.
Okay. Yeah.
Just to clarify, so monotone distribution, you mean everybody knows the ordering and then the PIs, the picture goes up, or so.
Yeah. So
It's not that there exists a.
yeah, exactly. Yeah. Everybody knows it's going to be based on the names. So it's going to be the numbers 1 through n. And actually, I'm going to, just for these slides, because that's how these slides are, it's going to be not monotone increasing, but non-monotone like decreasing actually, or at least non-increasing. Okay. All right. So let me just say that things for monotone distributions, we like monotone distributions because a lot of tasks are easier over monotone distributions. We also like them because the techniques we develop for understanding whether a distribution is monotone is oftentimes useful for other tasks. And we'll see that in a few slides. Okay, so monotone, thanks, Tony. What we mean by monotone is, in this case, and I'll change it later, okay? But in this case, I less than j implies piece of I at least as big as piece of j. Okay, so it's going down, but it's definitely not going up as you go to the right. Okay. All right. So what's the sample complexity of distinguishing p monotone from p epsilon far from monotone? It actually
L this or L1 distance.
in L1 distance, yes. Testing monotonicity requires root n over epsilon squared samples. Okay. Why? By reduction to uniformity. Because a distribution is uniform if and only if it's monotone increasing and monotone decreasing. Okay, so that's pretty easy to see. Slightly you have to do a few calculations, but not too hard to show is that you're epsilon close to uniform if and only if you're some like epsilon prime close to increasing and epsilon prime close to decreasing. So it's a characterization that's also robust to like modifications.
Is it a randomized algorithm?
So the algorithm itself is fixed because it just looks at collision or it does a reduction. But the only thing randomized is the samples you're getting. So this is deterministic. I know what you're asking. Sorry, it's deterministic, but it's okay. So the monotonicity tester gives you a uniformity tester with the same sample complexity. So any lower bound for a uniformity testing is going to be a lower bound for monotonicity testing. So that's just what we just said. And the question is, what's the upper bound? Okay, we know we need at least root n. Can we do root n? And it turns out we can do something like root n times log n. And it's open whether you can do root n over epsilon squared. Okay, I'm going to say something about these methods because it's cool. I'll say something. Okay, so the method of Descalakis, Diaconicles, and Cervedio used this idea of Berger, and what he said was that for any monotone distribution, you can partition the domain into these buckets. So like, I'm going to take the domain and partition it into segments, where the segments are getting exponentially bigger. Okay, so each segment is bigger than the previous segment by a factor of 1 plus theta of epsilon. So these guys are getting exponentially bigger. And that means because the segments are getting exponentially bigger, I don't need more than logarithmically many partitions. Okay. And then what Bourget showed and what these guys showed extends to this discrete case is that for monotone distributions P, if you take P hat, and what P hat does is it assigns the same weight to each partition, but then spreads it out uniformly. So like, let's say this was P, what P hat did is said, okay, here's a partition, spread it uniformly. Here's another partition, we're spreading the total weight uniformly. Okay, so that's P hat. It's an approximation that gives each partition, like conditioned on being within a partition, it's uniform distribution, but the weights of each partition are determined by P. Okay, and what they showed is that P hat and P are close to each other in L1 distance. I mean, if you pick the buckets in that way. Okay, and this is really cool. Why is it cool? Because you don't even need to see a single sample from this monotone distribution in order to be able to figure out this partition. The partition does not depend on P. The partition is oblivious. So this is wonderful. Okay, so that is and then what would your testing algorithm do?
And is this, okay, this is only true when P is monotone, right? This property that they prove.
Correct. And only monotone over the total order. Because later we're going to have problems over the other orders. Okay. So what does it say? For learning, it's enough to learn the weight of each bucket, and I'll just output P hat, and that's a good approximation to P. Okay. For testing, what I need to do, okay, what am I going to do for testing? Did I say that? Okay, okay, so we have a learning algorithm. Do we agree? We're just going to learn the weight of each bucket and output P hat. That's great. How do we get testing? We're going to learn P hat, which we just saw we can do, assuming it was monotone. And that just means estimate the weight of each bucket. Then we're going to check that P hat is close to monotone. Now, we don't need samples for this because we just have some numbers. Now, think about what might happen. P hat, it's not completely trivial, but it's not hard. Okay, because what's going to happen when you, let's say you took the uniform distribution and you took the buckets, it's not going to be exactly perfect, right? So it's going to go up and down. So you don't expect this thing to be perfectly monotone. So, but it's not a hard thing to do. You can do an LP or a brute force. The whole problem size is log n. You only have log n numbers. And you just have to figure out, is this thing close to monotone? So this is just like work, but it's not samples. Okay, and it's not even a lot of work because it's a problem of size log n. Okay, then you have to test that P hat is close to P. That's where you need more samples. And that's where you start needing root n samples, and you can reduce to the uniformity testing. Okay, so that's now you might have a question here. I'm just going to tell you it's okay in this case, but there might be some worry that maybe you need tolerance. You knew that P hat wasn't exactly P. So you need to pass if P hat and P are close and fail if P hat and P are far. And we said that that takes n over log n samples. In this particular case, it's okay. In this particular case, I don't want to get into it, but for technical reasons, it's okay. Why is it okay? Remember that we're doing non-tolerant testing of monotonicity. When we started this whole procedure, we only have to pass if the original P was monotone. We don't have to pass if it's only close to monotone. That actually helps us here somehow, but I won't get into it more than that. Okay, so let's talk about testing other types of shapes, not just monotonicity. Again, we're on the domain 1 through n, so it's total order. So we mentioned all these types of distributions, and what's common to all those classes that I had mentioned is that you can approximate all distributions in these classes by k-flat functions. Okay, so what we're going to do is we're going to take a class. Take your favorite class defined by shape, such as monotone, T-modal, monotone hazard rate, whatever you want. Show that it can be approximated by a log n flat distribution. And then our generic algorithm strategy will be find some k-flat partition of the domain. And this is something we can't use via Bourget because it's a little more complicated. So we can use an adaptive method that's from a different paper. And we can then estimate the weights of each of these k-flats. Then we can test that this learned k-flat distribution is close to P. And then we can ask, okay, so now we have this k-flat distribution that approximates my my original distribution. And now I have to just check, does this k-flat distribution actually have the property that I'm testing for? And that part is again, the part where we don't need new samples here because we just have to test if it's close to having the property. We just need an algorithm, okay? And in the algorithm, it just needs to be depend on k somehow. If k is logarithmic, it doesn't even need to be polynomial. Yeah, so that's the idea.
Okay, sorry.
Yeah.
Just making sure I got one part. So the k-flat partition of the domain depends on the input distribution that we're testing, right? It's not oblivious. And
No, it's not oblivious. I mean, maybe there's an oblivious way to do it, but this particular method, I mean, I don't think there is an oblivious way to do it, but maybe there's a less non-oblivious way to do it than what we do.
So how do you estimate the weights of them if maybe some of the parts are not very heavy?
Then, okay, great. If there's a section that's really not very heavy, I can just estimate it by 0 and it'll be close enough. And so if things that are really small, I can just estimate by 0 and forget about it. But that might make it not have the property, but here we're asking if the concise approximation is close to having the property. So we still have to pass even if it doesn't quite have the properties. So that's, so it works out, okay. Does that answer your question? Okay.
This is for the tolerant or the intolerant or both?
I'm talking right now, I'm totally intolerant.
Oh.
I'm very intolerant right now.
Can you say a couple of words of why this doesn't work? The tolerant?
Actually, I can't actually promise you that this wouldn't work.
Ah.
It's just not in the paper.
Okay. Yeah. I don't see an obstacle.
Yes,
That's
yeah.
and
Yeah.
I certainly don't know the technical details, but I don't see why it wouldn't work. For the
No,
tolerant.
I don't have a,
Okay.
no, we just didn't do it.
Okay.
No, it's a great question. I don't see anything. Okay,
And just
so,
to be clear, so in all of this, there's a fixed distribution that the algorithm knows, and then you do these steps. It's not.
no, it doesn't. It's a family, like I might say, it's a property, so it's like, there's a family of distribution that the algorithm knows, like monotone hazard rates. Or it's like, or T-modal.
Everybody.
Yeah, so let's take an example of T-modal. I know it goes up and down T times. So I might look for the T places where it goes up and down, and then for each one I may partition. And in between the places where it goes up and down, I may just use Berger partitions. Or I may use something fancy.
Was there a general characterization of when or at least one direction of what types of properties?
Right, so
You get that.
I mean, okay, I don't have a characterization. And is there a question?
Yeah, no.
Okay, good.
So how many samples do you need for the generic algorithm that you described?
Okay, it depends. What did I just do?
Yeah, this
Samples. Okay. The number of samples we need here is going to be root n plus something that depends on k. And the time complexity can get kind of hairy, so I don't want to talk about time complexity today. Forgive me, not till later. Okay. All right, so these families can all be tested with this paradigm. Some of these were already known, and one gets better, slightly better, or sometimes we just do as well as the best known results. And some of these have also been improved since this work by Canon. And what's interesting is actually Acharya, Daskalakis, and Kamat in a totally different paradigm attacked the exact same classes. I mean, they have another paper which is like a general purpose way of handling all these classes, the same classes, and completely different paradigm. So maybe it just says it makes sense to look at all these classes together. Whatever you do works for what works for one works for all. So that's, I guess, the message, one message. But I don't have an actual precise characterization of which classes it's going to work for. But if I were to come up with a characterization, it would have to do with how well the class can be approximated by k-flat distributions for this particular paradigm. Okay. All right, so up till now, everything has been total order, and I want to move to more general posets. Okay, so, I think you all know what a poset is, but I just want to point out that the size of the domain is still n. So now we're thinking of the domain as being like a graph on n nodes, and we're assigning probabilities to the nodes, and we're putting an edge between u and v if P of u is less than or equal to P of v. So that as you take edges, your probabilities only go up. Yeah.
I have a question about the previous slide. So if you can do it for two classes of distributions, can you do it for a convex combination of them? Is it closed under some operations?
I don't know. It's a good question, and I don't know.
Convex combination?
Convex, yeah, that's if you have with the probability that would have probability half its monotone, probability half its Gaussian.
Oh, I see.
That's a really good question. I don't know.
Then you can build more complicated ones.
Right.
Small.
That's a really good question. Wonderful.
This is a total.
Could you say something about the K-flat partitions or?
So I think a partition should survive, like if you intersect all parts of the first one with the second one.
Okay,
Like the size will be twice, it's fine.
okay. So then maybe yes. It's interesting. Okay, let's talk about it later, but I think it's a really good question. And
I was just asking, this is a total order, right?
it's partial order.
Why is it?
Okay, because these guys are not related. This could be bigger than this, or it could be smaller. I don't know.
Oh, okay.
Okay, so and now we're saying that P is monotone if where there is an edge between U and V, P of U is less than or equal to P of V. Where there's no edge, no constraint. Okay, so you can imagine on the grid, like a grid is a good example. Along any path, things are only going to get bigger. But I have no idea between these guys what the relationships are. Okay, and I'll show you pictures later of distributions on the hypercube where I just have no clue. Like sometimes one's bigger than the other, sometimes it's not, sometimes it's the opposite. So the only ordering I have is along edges. Okay, so we already saw that the line poset was like square root n. On the grid, for low dimensional grids, you can get something like square root n. This is work of a Daskalakis, no. This is Acharya Daskalakis Kamat. Looks at low dimensional grids and they get something exponential in the dimension. That's why I say low dimensional, but it's still interesting. And then you might say, okay, let me take the grid and put it on steroids and get the Boolean hypercube. What about testing distributions on the Boolean hypercube? And there things get, okay, so there's been a lot of work on that. And what I'm going to talk about, okay, so there's a lower bound in the work with Aliak Barpour et al. Of n to the 1 minus, is that right? Yeah, n to the 1 minus. So remember the n here is 2 to the number of dimensions in the hypercube. So this is n is 2 to the d, okay, times raised to the 1 minus theta square root of epsilon. So there is a pretty strong lower bound. And what I'm going to show you today shows that it can be done in order the domain size over log the domain size. So n again is 2 to the d, so it's 2 to the d over log 2 to the d. So,
Can you describe exactly what's the measure on the axis?
okay, the sample complexity.
No, I mean, oh, sorry. I mean,
Yeah.
Is it the relationship between D and D as a function of n?
Okay, so what this is this axis is n, the domain size, and it's asking how many samples do I need to test monotonicity over this domain? And we're saying that for like when we had the line coset.
So it's not. I see. I thought that this was like getting further away from the line by some measure having to do.
Oh, no, it's not. This is not the coset. This is the. Okay, thank you. What?
There is some colors, right?
Yeah. So it's no, it's just trying to say like, okay, we did really well on the total order. We got down to root n, and we're like, are all posets that easy? We found some other examples of posets, and they all seem to be sublinear in n, but we haven't definitely said anything for all posets. And just one really stupid poke set, the matching poke set, like who cares about that? It turns out to be useful for lower bounds. So, and also we exactly know what its sample complexity is. That's why it's so useful for lower bounds, but that's like another example of a poke set that we actually know. All right, let's talk about the hypercube because that's what I want to talk about. So I want to test, we want to test monotonicity of distributions over the Boolean hypercube domain. So that there's kind of a line of works that have looked at this domain. Again, what's confusing about it is the domain size is 2 to the number of dimensions. Okay, and the other thing I want to say is we're going to assume, I think everyone here has seen a Boolean hypercube, but I just want to point out that the arrows are going up. So these are like the smaller probability elements, and as you go up, you get larger probability elements. Okay, right? Okay, so there's a sublinear bound that was known before that and this is for any post set, if you can decompose it into a union of W disjoint chains of length L, then you can test with O tilde of W squared with L samples. And this is kind of an extension of the monotonicity testing result that we saw before. So it's basically saying, let's test that each of the chains is monotone like we did before. And then we have to check that they're consistent with each other somehow. And I'm not going to get into that, but it gives you something sublinear for the hypercube. Because remember, 2 to the D is the number of nodes. So it's something a little bit sublinear for the hypercube. Okay, but what we want is we want to get n over log n equals, so I probably should have used n here. So this is like, what this is really is n over log n raised to the 2.5. 0.25. And we want n over log n, not n. So we want something a bit smaller. So we're going to work really hard to get something a little bit better. So we want to go back to this learning testing thing. And our testing algorithm would look what we'd like to say is let's learn p hat, assuming p is monotone, check that p hat is close to monotone, and then test that p hat is close to p. Right? And that would be a good way to test. Okay, good. And now the question is, how do you learn, like before we had the Bourget thing on the total order, how do you learn over the hypercube with sublinear samples? And that's really what I'm going to talk about. But once you can learn, let's say we could do that. And by the way, it's not so trivial. Like the Bourget thing, you had this domain of size n, it was totally ordered, and you only needed polylog samples to test it, to learn it. Now we have a lower bound of 2 to the some constant times d. It's implied by these Tolerant-like distributions. So it's not so trivial to learn these things. All right. So this is work with my student Arsene Vasilian. We're going to show how to approximate. We're going to show first how to learn a distribution in sublinear time. I was given a monotone distribution. We're going to show how to learn it. And it's going to be in n over this thing that's actually a lot better than we need. So instead of n over log n, we're going to get over n over 2 to the log 0.2n. It doesn't matter what it is. The point is it's better than n over log n. Okay, that's all you need to remember. Okay, and then once we can do the learning, we're going to get the testing by checking that this thing we learned is close to monotone. There again, we need no further samples. It's just the linear programming. But sublinear time is open. So if you're looking for, I think this should be doable. If you're looking for open problems, there's one. And then testing that p hat and p are close to each other. Again, do we need tolerance in this case? It turns out we can do it if you can do it with n over log n samples. Even though it kind of looks like you need tolerance here, as we had before, but it turns out this using something similar to the valiant algorithm, you can actually do this in n over log n. Okay.
I'm sorry. So the thing that you said is open is given a distribution on the Boolean hypercube, test that it's monotone.
Yeah, given a distribution on the Boolean hypercube.
Random places in sublinear.
Okay, so we know how to test it with sublinear samples. What we don't know is sublinear time. That's what's open. Like we know how to do sublinear samples. But we just don't know how to do sublinear samples and sublinear time.
How is P-hat represented?
You can decide.
But I mean, your algorithm, what's it?
I'll tell you in a minute. But yeah, so we don't have a sublinear time learning algorithm. Okay, we actually do have a sublinear time learning algorithm for monotone because this thing, I think, it's not written that way, but I think this can be made into a sublinear time learning algorithm for monotone distributions.
It's just the sample complexity is not optimal.
Right, right. And so so I think what's open is n over log n samples and time. Even n over log n samples and sublinear time for learning monotone distributions. Yeah.
So this is still with testing monotonicity versus epsilon, bar, and TV from any monotone distribution, right?
Yeah.
But on a kind of general, like if I give you the exact distribution, is it like easy to compute the distance to a monotone distribution? And like all the n time?
No.
No.
No, that's going to take n over log n. So even for uniform computing, even testing closeness to uniform.
No, but I'm just not testing. Like I give you the exact distribution. Like,
Oh, I see. You want.
but I want to compute how close is it actually to being a monotone distribution.
Yeah, that actually can be done.
Okay, that's fine.
Yeah, yeah, that can be done. You mean like just by sampling and
No samples. I give you like the probabilities. I give you all the real numbers.
yeah.
And you want to compute like what is the TV distance from this exact probability distribution to.
Oh, so you mean poly and n? Okay, yes, that's doable. Yeah, yeah. Okay, good. I was confused because I'm always looking for sublinear in n. But yes.
Sorry, so it's.
So what's open here is sublinear in n.
Yeah, I'm not asking about the open.
But you're right. That can be done. Yeah.
And it's poly-n, it's n,
It's like n. I think you just go through and.
but if it's a post set, not a.
Oh, I see. Oh, okay, good question. Because a lot of times you have to solve some LP or something. I mean, that's the best way we know. And so depends on. I actually don't know the answer to your question, how fast it can be done. That's a good question.
But there should be some LP you can always write down for any post set.
Yeah.
Just
Yeah.
Maybe you can do better than that.
then, yeah, the objective changes.
Yeah.
Put the constraint.
Okay, so as far as samples though, it's n over log n samples for monotonicity. As long as we get this learner, it's less than n over log n, we're set. Okay, so how do we do the learner? Okay, I want to make just a definition. So in a monotone function, I want to define tight and slacky elements. So what's a tight element? So if f is monotone in the hypercube, that means like my probability has to be bigger than all my children, right? Now, if I'm exactly the weight of my largest child, then I'm tight, okay? So if I'm equal to my maximum child, then call me tight. But if I actually made a jump over my kids, you know, like I kind of, I have to be at least their max size, but I actually am bigger. So if I made a jump, then I'm slack. Okay, so for example, for the uniform distribution in the upper half of the hypercube, all the guys in here are tight because these guys are all probability 2 over 2n, 2 to the n. And so, you know, everybody's equal to the max probability of their kid. And these guys are all tight. All these guys have probability 0. And so they're, you know, they're exactly equal to the max of their children. The only things that are slacky are these guys on the border because their probability is 2 over 2 to the n, but all their children have weight 0. So there's, okay, these guys are slacky. Those are the slacky guys. All right, another, okay, that's, okay. So, all right, so let me just talk a minute about, forget about distributions for just 1 second and one slide, just like this bullet in the next slide. If f is Boolean, then the slacky elements correspond to DNF minterms, right? So like these guys, they jumped over their kids. They were like, okay, you know, I'm more than my kid. These are all zeros, and all these blue guys are ones. This is the Boolean function. So just like humor me for a second, and we move to Boolean functions.
So you mean a uniform distribution of the ones of the.
No, so no distribution, this is a function.
It's like zeros and ones.
Yeah, I'm just like, sorry, this should be F is a Boolean function. Just for a second, let's think about Boolean functions. These are all zeros, these guys are all one. Okay, so, because I just want to make the point about how it looks like DNF. So the function here is all zero and here it's all one. And these guys, they're bigger than their children, but everything in this blue shaded area has some child that's equal to one. Okay, so it's only these bottom points which define the midterms of a DNF that are slacky. Everything else is tight. So I think it's a good picture to have in mind so you can understand the rest of what's going on here. And in particular, this is a work in the Boolean, this is a function, monotone function, it's not a distribution. But in the setting of monotone functions, Blaise, Hastas, Cervetti, and Tan showed that for any monotone function, you can approximate it by a function G, which has its slacky elements only at specific levels. Like there's some constant number, but it depends on epsilon. Like something that depends only on epsilon, many green levels. And all the slackiness happens there. And this G is a good approximation of that. So they showed this lemma. This is a great lemma.
These levels are not oblivious, right?
No, I don't think so. Actually, I'm not sure. In that case, I think in their case, it's not, I don't remember. In our case, it's going to be oblivious. Okay, so this is true for Boolean functions. So remember you were humoring me and thinking about functions for a minute. I want to get back to distributions. So this can be extended to distributions. There's going to be, and you would want to say, this is what you'd want to say. You'd want to say that for distributions, it's also true, X is slacky and at most a constant number of special levels. And now instead of the noise, the noise being in L1 norm instead of just the number of Hamming weight norm, that's what you'd like to say, but it's not quite true. But the point is, don't worry about what it is, but you can make something close enough true. Okay, so let's just assume it was true and don't worry about this. Okay, I already see it saying.
No, I'm just, I was wondering also, you're saying that in the special levels, anything can happen, right? You don't have any restrictions on them.
Let me get away from that picture. I like this picture better. Okay, yeah. Anything can happen on the special level. They can stay the same as their kids, or they can jump, they can whatever they want. They can't get, it's monotone. They can't get less. They can't do that. Okay, but nothing interesting happens in between the green thing. Nothing interesting. Everything is tight.
All I'm saying is that it sounds weird that learning it would be possible in comparison to just checking monotonicity, because it could be that in the mid-level you have some completely arbitrary function, right? And then everything is still monotonic above it your ones and below it your zeros.
And chains, it's probably with the chains, not even.
Right, so
cut it into chains.
I mean, look, our learning algorithm is not going to be that good. So how many, are you worried about, there is a lower bound for learning that says, look, if I'm trying to learn perfectly, I have to get the middle level right, and they can be arbitrary.
Yes.
Even if I hit.
All I'm saying is it sounds like learning is much more difficult than testing.
Okay, but even that, like how many nodes do you have in the middle level? We're not going to even beat that. We're not going to come close to that. So we're not going to be so good that that's going to be a worry. I understand why you're worried. It's a good reason to be worried, but we're not even going to do that. Like, we're not even going to be that good.
So is the lower bound like n over third login? Or sorry,
Actually, the lower bound is something like
that's with the middle layer.
It's with Telegram functions, so it's like these. The lower bound looks like these kinds of things, but I don't think it's in the middle layer. I think it's in a different layer, and it's actually better. The lower bound is Okay, I wrote it here. This is the lower bound. So 2 to the d is n. So it's like n to the 0.15. So it's and right. And the number of things in the middle level is like 2 to the square root d, is it? 2 to over
2 to the over square root.
okay. So so the lower bound is less good. Okay. Cool. All right, so this is what we're going to use though, is that there's not that many, I mean, we can approximate f. Let me go back to the picture. We can approximate f by a function, by a we can approximate our probability distribution by another probability distribution where there's a small number of levels where things can happen. And in between, everything is kind of determined by what happened below. Nothing interesting can happen. Okay, so everything is tight in between these guys. And how are we going to use this in our algorithm? Well, here's a property of most nodes. Most nodes are kind of in between these green levels, and they're kind of pretty far away from the next lower green level. So there's enough space between x and here. Even if x is here, it's still got enough space that something good is going to happen. So I want that most nodes are kind of far from here, but here's good. It's just, these green guys are far enough away that even being 1/10 of the way is good enough for us. So I need that the distance from x to the next green is substantial. And then what we look, so because everything is tight, nothing exciting is happening between these green levels. That means that x is the max, not only of its children, it's also the max of all its predecessors on this line. Okay, so if you look, because nothing exciting happened. So x is the max of all of its predecessors. Let's say the max predecessor on this line was y, then what happens? Nothing exciting can happen. So all these guys have to be equal to P of y, and P of x has to be equal to P of y. So the probability distribution needs to be constant in this diamond.
Sorry, I think I'm just flipping with the word predecessor. Is it like just descendant thing? Like
Yeah. So let's assume that the probability distribution gets bigger as it goes up. So, but now, because nothing happened, and this was the biggest descendant of x, P of x has to equal P of y. And moreover, everything in the diamond between them, anything that's comparable both to x and to y. So it's anything that's bigger than y and smaller than x also is locked between them. It's sandwiched between them. Because anything on a path from y to x.
And there is no slack in any of them.
Yeah, because slacks only happen at green levels, and there's no green level there. So all of these guys are the same probability. And because x is kind of far, this is a pretty big diamond. So when you take enough samples, you're going to hit the diamond. Enough times that you can estimate the weight of the diamond. Okay, it's going to be uniform distribution. Everybody in there has the same weight. And it's going to be uniform distribution. All right, so what would my algorithm do? I don't actually know which is the largest predecessor. But let's say there's another predecessor, z. Okay, and if I look at the diamond between x and z, that may or may not be constant, because if the probability assigned to z was smaller than probability assigned to y, then some of these guys may have a lower probability. But then at some point when I start intersecting this diamond, then I bump up to this dark green weight. Okay, so that could happen, but
I'm sorry. How can it happen? Because there's supposed to be no slack here, right?
Yeah, but no slack just means you're equal to the maximum distribution, not the-
But if I'm on a path from z to x, at some point the probability increased.
but the guy on top could have other distributions.
right, if I get some guy that's also a parent of y, then I jump. Then I have to jump. But that's not called slack. So that's so the point is P's weight in the area between x and z is maybe close to that of y, or it might be a lot smaller, but it's never going to be bigger. Okay, So what the algorithm is going to do is look at all the predecessors of X on this level.
Algorithm for what?
Okay, now I want to learn. And I want to tell you, what is the probability assigned to X?
Mhm.
How am I going to do this? I'm going to go look at all of X's predecessors along this level. And I'm going to look at all these diamonds. That's a lot, but I'm going to do it. Okay, and then for each diamond, I'm going to look at the samples that fell into that diamond, use it to estimate, assuming it was constant on that diamond, I'm going to use it to estimate the probability,
So
the
you
average probability in the diamond.
you assume you know the green levels, and you assume you know that this is monotone, but you don't know the weights on the green levels. Just know what the green levels are.
Exactly. And then I'm going to estimate all these diamond weights. I'm going to pick the max one. The max one was definitely uniform because of what we just saw. The other ones I don't know. They might be close, might not be, but they're not going to be bigger. That's the thing I know. Yeah.
So I'm just a bit confused why you need the whole diamond. So maybe I'm misunderstanding something. So you have the level, you have these multiple green levels. Given an X, I know all its predecessors on the green level because I know what the level is. I just need to estimate the probabilities of those, right? Like, why is this whole?
I don't know that. See, I don't know their probabilities. So what I'm using is, I'm using the fact that this diamond, okay, this is the insight. I don't know P of Y. I don't know P of Z. What I know is if this diamond was constant and I had enough samples fall into it, I could estimate the average probability of everybody in the diamond. Now, I don't know which of these diamonds is constant. I have to choose between, but I know the max one was good. So I'm not going to be able to estimate P of Z from this, but I am going to estimate the max probability diamond is going to be good. Okay. So that's the whole insight. But the main thing is you don't have to do this for every, I mean, so what you're playing off of is how many predecessors do you need to look at? Because you have to estimate all those diamonds. And what's the, so you would like the green thing to be close to you, so you wouldn't have to look at too many predecessors. But if you pick it too close, then this weight is going to be too small and you won't have samples fall into it. So that's kind of what you have to balance.
So you are trying to learn the weights of the lower green level, not the upper one.
So I'm just trying to learn the weight of X, for example. But I can do this now for whatever X I want. So that's the basis of the learning algorithm. And it turns out that you,
But
Right.
the thing is that you need it to be sufficiently close to the lower level so that it doesn't have too many predecessors on the lower level, but sufficiently far so that the diamond is sufficiently large, so that sampling will hit it often.
Yes, but
But you're still trying to learn the middle, something in between the two lines, not on the line. On the line is way too hard.
So those are the only X's that can be higher, somewhere in the middle. That's the.
well, so now, okay, I mean, if I want to do Y, I can use previous guy. So basically, I'm going to take enough samples that all these max diamonds, or most of these max diamonds will be hit. Now, as I mentioned, we don't have sublinear time algorithms. We only have sublinear sample algorithms. So now I can take as long as I want. I can go for every X in the hypercube, I can go estimate its probability using this method. Okay, and most of the time I'm going to do well. You know, I won't do well maybe for the X that's right here because nothing's going to fall in their diamonds. So I won't do well there. Okay. And I'll just maybe assume it's something close and do whatever I need to do. But for most nodes, this is going to give me the right. Is that clear? Okay. So that's the idea. And so, I mean, we don't have type bounds for learning. We definitely don't have type bounds for testing. We don't have sublinear runtime. We don't have results for other domains like, like generalizations of the hypercube. So there's a lot of open questions here. In general, for arbitrary posets, these are the ones that have been studied. It's not that many. I guess one question is there a little O(n) sample monotonicity tester for distributions on any poset? And another thing you could ask is, what about the tolerant question? You were asking that before. So the tolerant question also, I think it's interesting even for the hypercube. We didn't get very far on that one either. Okay, I think I'm out of time, right? I still have half of my talk left. Oh. How much time do I get?
Would want to be done within 15 minutes.
Oh, hell, oh,
You
this is a
can
long
end early.
box.
You can end early.
No, I have more. Okay, cool. So if you don't mind, then I'll continue. Then, okay, so just for this section of the talk, I just wanted to say, for many problems, we need a lot fewer samples than you might think. And there's lots of cool techniques that people have come up with, and there's really lots more to do. Okay, so I guess that's part one of the talk, how to test your assumption. Now, the next part of the talk I wanted to discuss is what do you really need to test these distributional assumptions? Okay, how well do you need to test things? And let me take the case of agnostic learning of functions. So we're like off distributions right now. Okay, we're talking about function. You're learning a function. Now, what does a learning algorithm do? You get labeled samples, xi, f of xi, where f is assumed to be some class, like maybe monotone functions or convex functions or whatever you want to pick. And then you're supposed to output some approximation to the function that labeled those samples. But agnostic learning, you're given samples of some arbitrary function, g. It's any function. You make no assumptions about g. And you would like to label it with the best hypothesis from your class scriptf. And you can't always get the best one in scriptf, so you'd like to be epsilon competitive. You'd like to be within epsilon of the optimal choice. Okay, so is this clear? Or should I see? I think maybe you've all seen this, but if anybody wants, I can in more detail. All right. So here's the thing.
Always in studying the uniform distribution over the x's.
So at this level, I haven't yet said anything about the distribution. And this is a great question, Tony, because when you don't say anything about the distribution, I mean, agnostic learning, you're like, great, I want to agnostically learn. This is the holy grail. But the problem is it can be really hard. So convex sets, no finite sample algorithm, monotone, there's all sorts of lower bounds for agnostic learning. They're really terrible. Okay, but
Is that the distribution assumptions? Like,
I haven't gotten it. Next slide, here, good. If there's a distributional assumption, under a distributional assumption, things that were impossible can become just painful. And things that were really painful can become less painful. And sometimes they can even become doable. So if you can make a distributional assumption, then kind of agnostic learning becomes a little less formidable. That's the idea, okay? So, all right, but then, okay, so now, how do you use this agnostic learner? You run the algorithm on some data and you get some guarantee. Either this output of the agnostic learner is epsilon competitive with the best thing you had in F, and great, you can now rely on this output as your predictor, or the distribution that your data came from has nothing to do with what you assumed, and all bets are off, right? And then that's bad because you probably, not only do you want to throw out this hypothesis you just got, you may want to rethink your algorithm because it should be for a different class, right? And then it's not clear how to proceed.
But in the case of the distributional inputs, does that still happen? Wouldn't the distribution be related to the hypothesis class?
Well, so this is the one. If I had an agnostic algorithm that worked for any distribution, I wouldn't be putting up this slide. So it's when I make a distributional assumption, the question is, does it actually hold? So I'm making an assumption, I run the algorithm, and the algorithm gave me something. I'm like, okay, what do I do with this? Because if my distributional assumption held, which I don't know, then this is a great output, but I don't have a way of distinguishing the case where this is a great output from the case where I just picked the wrong distributional assumption and I should have used a different algorithm.
do you want to test whether the samples you get are according to the distribution or not?
So that I would like to do that, exactly. Okay, so I just want to mention a lot of papers do this kind of thing. But why would you not, now you'd say, okay, good. So let's test the distribution, then run the agnostic learner. But as you saw, testing uniformity takes 2 to the n over 2 samples, 2 to the dimension over 2. Okay, my n here is different. Sorry about that. I just realized it. All right, so let's just say this is no longer the size of the domain. Now that, okay, so it should be, those n's should be d's. Okay, so is this discouraging? Because this is I mean, the main point is this is much worse than the agnostic learning complexity. So in particular, like all the gain we got out of using a distributional assumption, we lost by testing the distributional assumption. So this is not great, okay? So the question is, just a minute. So here's the proposal. And that's to think of the tester and learner as a pair. So the idea would be this. Your data comes in, it runs through the tester. Now the tester may actually test something weaker than what you're assuming for your agnostic learner. But if it fails this tester, then it definitely doesn't satisfy the distributional assumption. So you just like get rid of it. You know, you forget about it. You're not using this algorithm. Okay, but if it passes this tester, it doesn't mean that your data actually has the distributional assumption, but it does mean the data is good enough for the algorithm. Okay, so it's good enough for the learner, and you can actually trust the output of this learner.
So you made the learner more robust.
And we make we actually try to figure out exactly what it is that the learner needs. We may change the learner, or we may say, I prefer to use this learner that has worse complexity because I can actually test that distribution. So the proposal is actually, let's compare not just algorithms for agnostic learning on their own, but algorithms for agnostic learning paired with a tester for what they need. So that's the proposal. Okay, so we want the combined runtime to be runtime and sample complexity to be small between the two of these. All right, so let me start with like a really simple example, just to illustrate that this could be possible. And you might say, okay, that's really, I mean, so this is super simple, but let's talk about decision lists over the uniform distribution. Do we all know what decision lists are? Okay, so let me show a decision list. A decision list looks like this. You have n variables, x1 through xn. And a decision list in general, like looks at the first variable, let's say x10, okay? And if it's 1, then I'm just giving an example decision list. It may say, you may output 1. And if it's 0, then you may look at x32. And then if that is 0, then you may output 0. And if it's 1, you may look at x12.
The same as decision.
It's a decision tree where you either output a leaf or you continue down the path. So it's a path. It's a decision tree that's equal to a path.
Okay. Sure.
Okay. So that's what it looks like. Now, you can just, it's easy to see that that there's an agnostic learner for this that just looks at the order 1 over epsilon degree Fourier coefficients and gives you a n to the order 1 over epsilon sample agnostic learner. Okay, so you can learn these. And it's n to the order 1 over epsilon. And this is agnostic. It's really easy to learn them. It's like order 1 over epsilon samples if you're trying to learn this in the non-agnostic case, in the realizable case. But it's even in the agnostic case, you can do it because you just need to learn the Fourier coefficients. It was like in the non-agnostic case, it was one of the first things there was Rivest's algorithm for decision lists. It's like the first thing you teach because it's so easy. It's really nice. That's okay. But here you just need Fourier coefficients, you can do it. And the thing you might notice is, look, this is what I would do assuming uniform distribution. But actually, if I'm estimating my Fourier coefficients, I don't actually need uniform distribution. It would have been enough to have k-wise independence for k being 1 over epsilon. That would have been enough. So maybe it's enough for me to just test k-wise independence for a k equal 1 over epsilon instead of testing full-blown uniformity testing. And it turns out you can do that in n to the order 1 over epsilon many samples because we can test k-wise independence much faster than we can test uniformity. Okay, so that's like a simple example, right? It turns out that for half spaces over Gaussian, you can actually almost achieve, it's not quite the same poly 1 over epsilon, but you can achieve something comparable with learner tester pairs. Even though testing Gaussian, there's like we don't know how to test Gaussian. So actually coming up with a tester of Gaussianity, we don't actually have a good tester for that. That's finite sample, but you could maybe come up with some notions of testing Gaussianity that you could do. It would still be exponential in n. But it turns out that for this algorithm to work, what you need to test is like n to the poly 1 over epsilon. Okay, and the insight is that the moments, the poly 1 over epsilon degree moments, all you need to test is that your input distribution has similar moments to what the Gaussian has, and that would be enough. And there's also a slight modification to the agnostic learning algorithm that has to be done in order to make this work. Okay, so that's something positive. There's also negative results, unfortunately. So just have to be on the table about this, that for learning monotone functions, even though there is a 2 to the order square root n over poly epsilon algorithm for learning monotone functions agnostically on the uniform distribution, doing this learning and testing thing requires 2 to the omega n. So it's not going to help for monotone functions. It's also not going to help for convex sets. So that's learning and testing for convex sets. Even though there is a good agnostic learner for convex sets, this kind of paradigm will not do for that.
It's like a conditional lower bound, or
No, this is like this is a sample lower bound. But just the proposal, the old way of doing tester learner pairs that may work, that still works, is compare agnostic learning algorithms based on their sample and time complexity, and pray that your distributional assumption holds. And the new proposal would be compare agnostic learning algorithms based on their combined sample, time complexity of the learner and tester. And you may need to modify your agnostic learning algorithms to be compatible with the tester. So that's sort of the, so to conclude, full-blown property testing is not always necessary, but sometimes it is, it depends. And there's really lots of open questions. Now I'm done. Okay.
One thing that occurs to me is like this work that's old now of getting new learning algorithms using sum of squares, like that whole machinery. I mean, you would think that is another way to see that what you're testing is like a more formal way to see that what you're testing is.
Actually, that's a good point. That's interesting. Yeah.
How,
So it's like, so essentially saying
look at the specifics of what you're.
the moments are everything.
Yeah, exactly.
Yeah.
any interesting properties that you can test in like much smaller than square root n, like polylog or?
No, I don't have an example of that.
In practice, like square root n would already be probably too big.
Right. So this is the problem with, okay. So I think, let me step back for a second. I think the question is, these bounds for distribution testing are kind of horrible for people. And because I mean, the point is we're looking for sublinear in the domain size, but then we have these lower bounds that are atrocious. Right. And so I think that's what you're saying.
Oh, yeah, any part of this could be like practical, like really sublinear.
So I'll tell you what I mean, okay.
No,
Good question. The one thing we actually do is like, we assume less, like we assume something, but we assume less. Like I may not assume that it's Gaussian, but I may assume like something about how modal it, like that in any, that it looks, let's take Gaussian over one dimensional. Instead of assuming it's Gaussian, maybe I'll assume it's bimodal, and then test that it's Gaussian, for example. And that would be a lot easier. Like that could really bring, if I would assume something, but I would assume something less strong. And then there has been a bunch of works on that kind of thing. And those are often much easier. So that is one approach. Other approaches would be assume you have an oracle. So this is an approach that I used to like. I mean, I have papers in this, but I was like, I'm not sure why we worked on that, because where are you going to get this oracle that tells you not just an oracle for samples, but also an oracle that tells you what's the probability of P of X for a given X? Like, why would you have this oracle? And I thought, I'm working on it because it's fun and like the student is interested, so cool. And But no, you're never going to get that oracle. Turns out, so I was wrong. Because it turns out there's this whole area now of learned algorithms, and you can learn an oracle. Sometimes you can learn an oracle that learns, like, that will answer queries about, you give it input domain element X and it tells you P of X, but it actually doesn't tell you P of X, it gives you an approximation to P of X. And you can actually use this type of learned oracle to help you say things about the true distribution, not just, I mean, the learned oracle gives you an approximation, and you can still use it to help you say things about the true distribution. So there are works like that too. And then there's other works where people just look at different distances, like L2 distance or EMD, or there's a bunch of other distances that people look at. So that's kind of how we get around the fact that these are horrible sample complexities.
And L2 you can do better.
L2 is so much easier because L2 doesn't really say anything. So it's really surprising. You can test the L2 distance to uniformity in like 1/epsilon squared time. And you're like, wow, that seems too good to be true. It must be wrong. But then you're like looking at what does that actually mean? And then you see that there's these distributions that you wouldn't call them close to uniform. In L1 distance, they're super far from uniform, but in L2 distance, they're close. So it really, so I guess if you're used to thinking in L1, then you're like, L2 doesn't mean anything. But if you're not used to thinking in L1, then testing L2 is much easier. So I guess it all depends what you think. I mean, because you can come up with distributions that share no support, nothing, and their L2 distance is close. It's really easy. Like take the distribution that's uniform on the first n/2 elements and take the distribution that's uniform on the last n/2 elements. They have nothing in common in the support, but their L2 distance is actually really small. So, so I think that's an example of why L2 testing becomes easy. But still, people do it in the database community. They do it. So. Also, if you have some assumption on continuity or something like that, then that might also help. So basically, that's how people try to get around it that I've seen.
So we're going to ask questions for lunch, and thanks, Ronitt. Thanks for a good.